All right, we're going to look at something that I've put together here. And the idea is to have two radios for winter field day on the same band, the same mode, operating just a small frequency range separate from each other, two different antennas, and to have the ability to null the one transmitter's out from the other's receiver and vice versa. So this is going to take a bit of work to do, but here's the basics of it. If you look at this diagram, on the bottom left would be the transmit radio. It would be a 100-watt radio, which is the maximum allowed for winter field day under the new rules. And there would be a sampler that would take a small section of that transmit signal off and when it's transmitting, and feed it into a variable attenuator with increments of down to 1/10 of a dB, which is normally about the smallest that they make them, and then have it run through a delay box of a specific number of nanoseconds, and then inject it back into the receive path of the second radio out of phase with it to create a null. And let's see how that would work. So if we take that sample, and at the same time that sample is being taken off, the transmit signal is going to the transmit antenna. Through the air, it's going to couple into the receive antenna. It'll be down a number of dB, but it's still going to be quite strong and easily overload the receiver on the second radio. So there is a delay between the time it leaves the transmit antenna and the receive antenna, and that's down in nanoseconds. It's about 1 nanosecond per every foot of distance between the two antennas. There obviously will also be delay in the feed line between the two, whereas the sampler is not going to have all that. So the feed line is represented by that large arrow on the left and the large arrow on the right. The smaller ones on the left and the right are going to be just a short jumper between the transmit radio and the sampler. So then that amount of delay, including the coax length delay, is going to create a delay coming back into the receive antenna, or actually into the receiver. It's going to hit a combiner where it will take the delayed sample from the transmitter and mix it with the transmit signal coming through the receive antenna, and hopefully achieve a null by making it the same level and also 180 degrees out of phase. So you can see in the center where it says adjust attenuation and delay, or the phase, for a null. If you can achieve that null, then that signal coming from the transmitter will effectively be reduced to a very, very low level so that it does not overload the receive radio. That null will change quite easily as the frequency changes. You can make that null quite steep, but if you just change 1 kc on the transmit side, it's going to increase a little bit. And when you do several kcs, it's going to start increasing a lot. So it's still going to be, even if you go 100 kcs away, it may still be 30 dB or more, which might be enough to prevent overload. But you can achieve a lot more than that, 60 dB or more, if the transmit radio is on a specific frequency. And then if you made the TX sampler and the RX injector so that they had the same amount of attenuation, in theory, this delay box and variable attenuator would work in both directions. So you'd probably want to set it for a frequency between the two radio frequencies that you're going to operate on. But in this arrangement, there's another feature that you could use, and that is to use the second radio as just a spotter for the first one. Anyway, that's the principle behind it. Okay, we're looking at a IC705 with a signal generator feeding it two different signals. One is simulated through an antenna path with I think 30 dB of attenuation and an amount of delay equal to maybe like 30 feet of antenna separation. And then the other one takes the same signal and feeds it through out of phase through a variable attenuator to try and match that, but exactly 180 degrees out of phase and at the same level. And let me show you how much signal decrease we get when we do that. This signal is almost 40 over, and when I put that delay unit in, it goes down below S1. I mean, there's virtually no signal there whatsoever. So, I mean, that's like 90 dB or more. So that will only work at a single frequency. As soon as you move off that frequency, it's going to increase. But still, that's a huge amount of attenuation because of a null. I mean, you can still hear the signal because of the AGC. On the receiver, it doesn't sound that much weaker, but you can see the difference between basically an S0 signal that you can still copy and almost a 40 over signal without the null in there.